Hi, my name is Janos. I'm a PhD student at University of Cambridge, working with and for materials project, and I'm here to tell you about a new machine learning evaluation framework we've developed for material stability prediction, which is named Matbench Discovery. We designed a task to closely simulate the deployment of machine learning energy models in high throughput searches for new inorganic compounds. And our goal in this work is to answer the question, which machine learning methodology performs best in a prospective discovery setting, and also to establish a yardstick by which to measure future progress. This work was largely inspired by two earlier efforts led by Chris Bartel and Alex Dunn from 2020. The first one on the left is called Matbench, which is the namesake for this project. And it was a collection of 13 standardized data sets along with canonical cross-validation splits for consistent model evaluation. And this was really the first sort of online leaderboard that allowed to compare state-of-the-art models on a fair benchmark against each other and see how far and how fast the field had come. However, it focused solely on property prediction of known materials, and we see materials discovery as a missing piece here, since machine learning is a very high throughput method and perhaps even more useful for searching the huge space of possible materials than for property prediction of known materials. The second work we build on top of is the Bartel 2020 paper on critical examination of compound stability predictions from formation energies predicted by ML energy models. And Chris found that he deployed a bunch of models, found all of them to provide useful accuracy in formation energy predictions. But crucially, when asking those same models to predict crystal stability in the form of decomposition enthalpy, you can see on the right side plots here that all of their performances degrade sharply. And this revealed that machine learning models are much less useful than DFT for discovering new inorganic compounds than perhaps prior studies had suggested. And this is where Matbench Discovery comes in, as a new evaluation framework for measuring true model utility in a prospective discovery setting. And you can see in this flowchart what a submission to our leaderboard would look like. You start by training your model on the latest Materials Project 2022 release, containing a total of 154,000 crystal structures. You're free to train on all data available from Materials Project, including relaxed and or unrelaxed crystal structures, as well as the DFT relaxation trajectory between them. And once your model is trained, you deploy it on our test set, which we refer to as the WBM test set, which was generated by Wang et al. In 2021 by taking Materials Project source structures and applying to them a chemical similarity matrix, which they data mined from the ICSD to perform single element swaps. So they input a crystal into this matrix, and it'll replace a single element, usually by a chemically similar one, to generate a new structure. These new structures, they then relaxed with DFT to check for stability and generated a total of 257,000 novel compounds this way, of which they found roughly 43,000 to be stable with respect to the Materials Project convex hull. So the task for any model on our benchmark is to try and recover as many of those 43,000 stable structures as possible, while committing as few false positive predictions as possible. So once you have your model results on our test set, you can rank them all by stability and apply a set of analysis scripts to them that we provide. And these scripts will generate output files, which you can then push to a GitHub PR, which we will review and merge, after which your model will appear on our leaderboard and, with any luck at all, be crowned perhaps the new king of machine learning for materials prediction, stability prediction. So to answer the question, which type of model architecture performs best at materials discovery, we've already submitted a total of 8 different models covering a wide range of methodologies to this workflow, or to the flowchart outlined on the previous slide. And they're all ranked in this table by their F1 score. You can see that we have everything ranging from random forests to single-shot GNN predictors like Magnet, CGCNN, as well as CGCNN plus P, which uses random structure perturbation to augment the training set. We also have a crystal symmetry transformer, which is called RenFormer, an iterative Bayesian optimizer, and universal interatomic potentials like ChargeNet and M3GNet. This heat map ranges from yellow, which is best performance, to blue, worst performance. And we focus on 6 classification metrics on the left-hand side of this table here. But we also show 3 very commonly used regression metrics on the right-hand side. ChargeNet from Bo and Deng et al. Is currently the state-of-the-art model on our benchmark, achieving an F1 score of 0.59 and a precision of 52%, meaning more than half of its stable predictions are actually stable according to DFT. It also achieves an impressive discovery acceleration factor of 3.06. And what this number measures is how many more stable structures does a model find compared to dummy selection on our test set. And you can see the dummy discovery rate would have been 16.7%, given 43K out of 257K stable structures. And so the maximum possible discovery acceleration factor is 1 over this number, or roughly 6. So ChargeNet is already halfway at optimal performance, or nearly halfway optimal performance on our test set, suggesting that in the future, we will want to construct even more challenging crystal stability prediction benchmarks. Let me also highlight a sharp disconnect between the regression metrics on the right and the classification metrics on the left, especially for some models like MagNet and CGCNN, which notably perform worse than dummy performance. In the bottom row here, you see dummy performance, which is achieved by always predicting the test set mean for every material. And even though MagNet and CGCNN are worse than dummy regressors, they are clearly significantly better classifiers than the dummy classifier, which really highlights that perhaps the field has been focusing on the wrong metrics to optimize all along, since these metrics are very prevalent in the literature, but arguably much more indicative of true model utility are these classification metrics, which we focus on. In this plot, we illustrate why the interatomic potentials are such reliable stability classifiers. What you see here is the rolling MAE for predicted hull distances from all models on the WBM test set as a function to the DFT distance to the MP convex hull. And so you can imagine towards the left-hand side of this plot, you see the error that models commit on very, very stable structures, whereas on the right-hand side, you see model errors for very unstable structures. And the middle right here, all models achieve roughly their lowest error at the stability threshold of 0 MeV above the hull, which is also where the mode of the Materials Project training set is. So this is not surprising. Note that we have highlighted this red triangle, which I like to refer to as the triangle of peril, since as long as a model's line remains within this triangle, its average error is larger than the distance of this prediction to the classification threshold. And so that means the average model error is large enough to invert a classification from a correct one into an incorrect one. So really, a model is more reliable as a classifier when it exits this triangle of peril early. And you can see on the left-hand side, the model that does this first is ChargeNet. And on the right-hand side, M3GNet actually exits first at a very low, just 40 MeV error above the hull. So any classification it makes for a structure that's more than 40 MeV unstable, you can be fairly confident that it is correct. Notably, though, it's overtaken by Renformer for very unstable materials. And so you would expect both Renformer and M3GNet to commit fewer false positive predictions. These two plots show the cumulative precision and recall over the course of a simulated discovery campaign. In both cases, the higher a model's line in these plots, the better. And we generate these lines by having all models rank their stability predictions for each model, and then just going down that list of materials one by one. And at each step, checking, is this a correct classification? If so, the cumulative precision line stays flat, and the recall line goes up a bit. If it was a false positive prediction, then the precision line drops slightly. And if it was a false negative prediction, then the recall line stays flat. So a line terminates when a model stops predicting materials in our test set as stable, which explains why all of these lines have different lengths. And you can see this dashed vertical line shows the true number of stable materials. So notably, all models overpredict the total number of stable materials in our test set, some by a significant margin, like Renformer by more than 100%. It just so happens that on our test set, ChargeNet happens to be the best model across the entire range of this x-axis. But if you look at some of the worst performing models, you see that in principle, these lines can cross, in some cases even multiple times, as is the case for a magnet and Randformer, for instance, suggesting that in principle, which model you pick for your discovery campaign depends on the scope of your effort. So how many how many machine learning predictions you can validate. In conclusion, we found that some models exhibit a sharp disconnect between regression and classification metrics. And while regression metrics are what perhaps the field has focused on more in the past, we think that classification metrics are actually much more indicative of actual model utility, at least for stability prediction. And we also found that universal interatomic potentials, so models that include forces and emulate DFT relaxation, clearly emerge as the current state of the art for materials discovery. They show remarkable accuracy and robustness across a wide range of chemistries. So our main take-home message is a bit daring, but hear me out. We think that based on our results, it appears that machine learning for materials discovery is at a similar inflection point as OpenAI was after Google published the Transformer paper in 2017, which is to say we now know which is the winning architecture. We just have to scale it up and feed it much more data. And we believe that this could lead to a foundational model that can cover the entire potential energy surface at useful accuracy and provide answers to materials properties and stability questions in a matter of seconds or mere minutes. Coming to my last slide here, I'm happy to say we're now open for business. Matbench Discovery will be accepting new model submissions starting today. We have an interactive leaderboard up at matbenchdiscovery.materialsproject.org where you can find much more details on how each of these models perform, as well as their methodology. And we also have docs on how to submit new models. We also have a PyPI package, which you can pip install with Matbench Discovery that helps with downloading and caching our train and test sets, as well as analyzing your model predictions. And last but certainly not least, let me thank all my collaborators, in particular Reese and Anuba for help with conceptualization and analysis, Christine for hosting me at LBNL while I was working on this, and Alpha Lee for being a very patient PI, as well as these kind people for very helpful discussions, and these institutions for funding and compute. Thanks for coming, and I'm happy to take questions.